All right, everyone. We're going to cover 11.9 in this video. First, a little recap from 11.8. So from 11.8, we know there are these things called power series, right? Um, they have the same attached questions as regular series. We ask if they converge and what do they converge to, etc. And we found out, okay, well, they're always converge at x equals a, right? Okay. And then they might converge elsewhere. They might converge everywhere. They might converge on a finite interval, or they might only converge at that point, x equals a. Okay. They might have interval of convergence. I guess we could say they always have an interval of convergence. Sometimes that interval is, just a single point, or it's, a finite interval, or it's the whole real line. Okay. And then what's going on that interval of convergence? Okay. On the interval of convergence, um, my power series is a function. So meaning I plug any x in. If the x is in that interval of convergence, I can plug the x into my power series and I get a value out. So it behaves just like any other function of or any other function of x we've seen before. I plug in an x and I get a number out, right? So on the interval of convergence, the power series is a function. And maybe I've written a complicated power series, but it's actually equal to a familiar function, may equal a familiar function, meaning like something we've seen before, like e to the x or sine of x or tan inverse of x or what have you. Okay. So this is kind of where we're at. In the previous video, we kind of tackled the first couple questions. We talked about when and where is the series convergent. So the power series convergent. So in the previous section 11.8, that was all about finding the interval of convergence, radius of convergence for the power series. So that tells us where the series converges, but what does it converge to? Okay, so what function is the power series equal to? And maybe I have a function in mind and I want to create a power series. So 11.9 and 11.10 are uh, they're kind of about making specific power series for functions. So making, having a function in mind and making a power series for that function. So that's kind of like what function? What function does the series represent? So that's where we're at. In 11.10, we're gonna figure out how, like, we're gonna start with a function in mind and create a power series for it. 11.9, we're gonna do something similar, but it's not as it's kind of a shortcut, but it's not. We can't use it all the time. Okay, so 11.9, we're making we're making power series for functions by, we'll call it modifying a known power series. So what I mean is, maybe we don't know how to make a power series for sine of x or e to the x, or maybe I don't know how to start with a function and make a power series for it. But maybe if somebody gives me a power series for another function, I can modify it a little bit to get a new function, maybe a function that I want. So that's kind of what we're gonna do in 11.9. All right, so let's start looking at the easiest way to modify a power series to get new power series for different functions. Okay, and we're gonna work with the power series x to the n. Okay, this familiar power series, we're saying this power series equals 1 over 1 minus x. And remember, this is just on the interval -1 to 1 on this interval of convergence, right? Now, what if I wanted to find the power series for 1 over 1 plus x? Okay, what's the power series for this? Since this is so similar to this function, we expect maybe the power series are going to be very similar. Okay, well, let's rewrite this to get this function to be very similar to this function. I can rewrite this as 1 over 1 minus negative x, right? So how would that change the power series? Okay, the only difference here is, let's see, I'm looking at these two now. I have 1 minus x here, and in this function I have 1 minus negative x. So it should be that for the power series, what should be different about this power series? I should replace the x with negative x. And then I could maybe simplify this power series a little bit. I could say, this power series, I could bring this -1 out, and I could say this is the power series -1 to the n, x to the n. Okay. I think either one should be acceptable. Okay. So we see, it's a very easy modification to get a power series for this new function, 1 over 1 plus x, right? And we can do other similar modifications. So again, I'm working with, okay, x to the n equals 1 over 1 minus x. Okay. What if I wanted the power series for 1 over 1 minus 3x? Okay. I should just replace x with 3x in my power series. And again, I could simplify this. I could say this is, or, kind of maybe split these terms up. I could say this is 3 to the n, x to the n. If I wanted, again, either one should be fine. Okay. So in general, again, working with this familiar power series, whenever I have whenever I'm trying to make a function, a power series for the function 1 over 1 plus something, I should try and rewrite it as 1 minus something in parentheses. So for example, going back to that first example I did, I was trying to write 1 over 1 plus x, a power series for this, right? And then so I rewrote it as 1 over 1 minus negative x. And then this stuff in parentheses, I'm just going to replace my x in my power series with whatever's in parentheses. Okay. So I'll show you what I mean. Let's say I wanted to write a power series for 1 over 1 plus x to the 4th. How about that? Well, I'd try and get it into a similar format as this. Okay, so I do 1 over 1 minus, and then what do I need inside the parentheses? I would need negative x to the 4th, right? And then, okay, so I'm going to write up the power series, and I'm going to replace my x with this, whatever's in parentheses, negative x to the 4th to the power n, and I could split that up. Let's see, I got negative to the -1 to the n, x to the 4n, So I could write it like this. And again, these are the same thing. What if I have something a bit more complicated? What if I want to find, let's, write our original power, our standard power series. And what if I want a power series for a function where I have something on some x's on top and bottom? What if I have something like, what if I want to write a power series like this for a function like this? Well, what I would do is, again, I want to try and match it up to this, but I got an x to the fourth on top, right? Okay, so that's a problem. So what I'm going to do is I can rewrite this as x to the fourth times 1 over 1 plus 7x, right? Okay, so I'm going to, if there's something's on the numerator, I'm going to kind of pull it out, and I'm going to try and write the rest in the rest of my function in this form. So I got 1 over 1 plus 7x. Now let's try and write this piece in a form similar to this, okay? So I got my x to the fourth out front, and then I would have, okay, I want this to be a minus, and then what do I need in the parentheses? Negative 7x. Okay, so now this thing has a power series, right? I know the power series for this thing. Okay, the power series for this thing is, okay, I'm just going to replace x to the n with negative 7x to the n. Okay. And then what do I got? I still got an x to the fourth out front, right? That's from here. Okay, so I got x to the fourth times this thing. Okay, and now I'm just going to I'm going to basically pull the x to the fourth inside. Okay, and if you want, we can simplify this one a bit first. Okay, so let's come over here where there's a little room. Okay, I got x to the fourth times negative 7x to the power n. Okay, I can split these two terms up. Let's see, I could write this as negative 1 to the n, 7 to the n, x to the n, right? If I just wanted to split this up completely. Or I could do a negative 7 to the n, x to the n. And then when I pull the x to the fourth inside, okay, what's going to happen? I'm just going to add 4 to the n, okay? So negative 1 to the n, 7 to the n, x to the n plus 4. And then everything's inside my power series. So this is my power series now, and I'm done. Okay. So not too bad, right? So these are the first tools in my toolbox for modifying power series to get new functions. Okay, a word of warning when we modify these power series to get power series for new functions. It can affect the radius of convergence, interval of convergence. So for example, let's go back to one of the examples I did earlier. Okay, we started with x to the n equals 1 over 1 minus x, right? And from this, I want to define the power series for 1 over 1 minus 3x, I believe. Okay, so we said, okay, well, we're just going to replace the x in our power series with 3x. So we ended up with this power series. Excuse me. Okay, which we could simplify as 3 to the n, x to the n. Okay. Let's see. This power series has, we've seen this before, has an interval of convergence negative 1 to 1 and has radius of convergence 1. Is the same true for this series? Okay. Let's double check. How do we double check? By the ratio test, right? So I want to do an plus 1 over an. Okay. That's going to give me 3n plus 1 x to the n plus 1 over 3 to the n x to the n. I simplify, I get 3 times x, and I want this to be less than 1. I want this limit to be less than 1. So what do I need? I need 3x to be less than 1. In other words, I need 3x to be less than 1, greater than negative 1. X is less than 1/3, greater than negative 1/3. Okay, so we're already seeing a different interval of convergence, right? The interval is going to be negative 1/3 to 1/3, and we need to test the endpoints. Okay, let's see what happens when we test the endpoints. Okay, I'd plug negative 1/3 in here, and what would I get? The series would simplify as negative 1 to the n. This is divergent by divergence test. Okay. Again, we would need to show this more carefully, but hopefully you guys can see that. Now I'm going to check x equals 1/3. Okay, when I plug that into my series, I get just 1 to the n. Okay, this definitely diverges, right? Again, by divergence test. Okay, so I don't want to include those endpoints. So my new interval of convergence is negative 1/3 to positive 1/3, parentheses on both. And then what's the radius of convergence? That is also 1/3. Okay, so my original power series had this interval in radius of convergence. My new power series has this interval, radius of convergence. Okay, so let's see, we found a power series for this function, 1 over 1 minus 3x, by modifying our original one. But this power series representation is only valid on this interval of convergence, right? It's only valid here. If we go outside this interval, it's no longer true that the function 1 over 1 minus 3x equals this power series. So be careful with these modifications. We got to check the new interval of convergence and radius of convergence. Luckily, there are other techniques where nothing, the interval, the changes aren't as severe. So we're going to introduce some new techniques next that will be a bit different in how we apply them. Okay. But hopefully you guys understand these basic modifications. Again, I'll do a problem video where I do problems from 11.9, and I'll use all the techniques and give you guys some more examples. But let's go ahead and introduce a new technique, and it stems from Theorem 2 in section 11.9, which I'll write out right now. Okay, so this is Theorem 2. So let's go ahead and read through this, and I'll explain what it means afterwards and how it gives us new tools to make new power series. Okay, so if the power series Cn x minus a to the power n has a radius of convergence r greater than 0. Okay, so we don't want to deal with the power series that are just convergent at a single point. We want it to be convergent at least on a finite interval, and the entire real line is even better. But okay, let's say this power series has radius of convergence r greater than 0. Then the function f, defined as f of x equals the power series, is differentiable on the interval a minus r to a plus r. Again, this might be negative infinity to positive infinity, or it might be just that finite interval centered around r. Okay, then what do we have? We have f prime of x equals n cn x minus a to the power of n minus 1. And maybe that looks real complicated, but think about derivatives, right? Look at this power series and think about it. If I wanted to differentiate each of these terms in the series, what would I do? I would bring, this is a x to a power n, right? With a constant out front. If I wanted to differentiate that, I would just bring the n down. I would have n times cn, x minus a, and then I would have n minus 1 here. And that's exactly what I have here. Okay, so let's say I have a power series and it's got an interval of convergence. And on that interval of convergence, I know it's equal to some function. Okay, then if I want to find the derivative of that function, all I need to do is differentiate the power series term by term. Okay, So let's say I had, a quick example. I said x to the n equals 1 over 1 minus x on its interval of convergence, right? What if I wanted to find the power series for the derivative of this function? Okay. Let's see, the derivative of this function would just be 1 over 1 minus x squared, right? So what if I wanted to find the power series for this? Okay, well, since this is the derivative of this, then the power series should just be the derivatives of these. Okay, so the power series should be what? N x n minus 1. Okay, so that's the tool we're developing here. Okay, let's continue reading through the theorem. Okay, so we were here at number 1, and we said, okay, the derivative of f is just the derivative of the power series. Okay, and what's number 2 say? The antiderivative of f, the indefinite integral, uh, this is the antiderivative of the power series. Look at this power series, my original power series. If I wanted to integrate this, if I wanted to integrate the terms inside, these individual terms, what would I do? Again, I have x minus a to the power n. What's the integral of that, the indefinite integral? I would add 1 here, become n plus 1, and then I'd divide by n plus 1, right? And that's what I have here. And remember, when I integrate, I have a constant of integration, right? I have integral, is some function plus c, okay? So this is that plus c, all right? So I got my power series, and then I got a big plus c that's separate from the series. All right. And in this, using this tool, the radius of convergence doesn't change, which is different than what we were doing in the previous modifications, right? The interval of convergence and the radius of convergence changed in my previous examples. But here, my radius of convergence doesn't change. I still need to check the endpoints, because let's see. My power series, all my statements are just about what's going on in this interval with parentheses on both sides. Maybe this series, okay, maybe it's actually convergent on this closed interval, but we always deal with these open intervals with parentheses. Okay, I know at the very least my new series is going to be convergent on this interval as well, and then maybe this new series, maybe it's actually going to be convergent on a minus r to a plus r parentheses, something like this. And it could be different. These end caps could be different than the end caps for my original. So I need to check my end points for my new series to find my new interval of convergence. But the radius of convergence will be the same for my new series and my old series. So let's see, again, I think this is clearer if we see an example. Let's go ahead and see an example. Okay. So the one I did for the derivatives is I said, okay, we had our original series x to the n, okay, equals this function. Let's stick with this one for now, and we'll do a couple more. What if I wanted to find the power series for f prime equals this? Okay, well, we can forget about this. Well, this function is the derivative of this function, right? So power series for this should be the derivatives of this. Okay, so we differentiate term by term. When we differentiate all the pieces of the power series and write it like this is called term by term differentiation. Okay, so my new power series is this. Now it should have, let's see, this had an interval of convergence -1 to 1 with parentheses on both sides. The numbers should be the same. Let's check whether whether these are going to be parentheses or brackets. So how do I do that? I plug these values into my power series and see if it converges or not. So I plug in -1 for x, and what do I get? When I plug in x equals -1, I get this power series. And then this is divergent by divergence test. What if I plug in x equals 1? Then I get the series positive 1 to the n minus 1 n. Again, this is divergent by divergence test. Okay. So I don't want to include these endpoints. All right, so boom, parentheses on both. So in this case, the interval of convergence is the exact same for both, and the radius of convergence is always going to be the same for both. All right. One thing that sprang to mind, if you're looking at this notation here, our original series starts at 0 and this new series starts at 1. Don't be freaked out by that. It's just because look what happens if we start this series for derivatives at 0. It would be that my first term would be 0 times C0, right? So the first term would just be 0, okay? And then I'd have C1 x minus a to the power 0, and then, and so on, okay? So this would be the series started at 0, okay? But since that first term is 0, it, it doesn't affect the series at all. So I could just say it's the same thing as starting at 1. Okay. If you prefer to keep it at started at 0, if you prefer to write it like this, that's fine. But it, you can do it either way. Okay. So now let's see some more examples of using these techniques to find new series. So I have my kind of standard series. What if I wanted to find the power series for negative ln 1 minus x? Okay. Well, let's look at this. How is this function related to this? That's kind of, when I'm using these integration and differentiation techniques, I kind of ask myself, is this the integral of this function or the derivative of this function, or somehow related to that? So what I do is I look at this a bit closer and I see, okay, this is actually the integral of this function, right? We can check that real quick. Integral of 1 over 1 minus x dx. I do a u sub. Okay, yeah, that's negative ln of u plus, well, I'm going to leave the plus c off for a second. Undo my substitution. Okay, yeah. Okay. So this function I want to find the power series for is the antiderivative of this. So I should be able to just integrate this series term by term. Okay, so let's do that. Integrating x to the n would give me x to the n plus 1 over n plus 1, starting at 0. And then remember, when I do indefinite integration, I would have a plus a constant, right? So I'm saying that this plus c is going to equal negative ln 1 minus x. Okay. Now, what do I do about this plus c? I'm actually going to solve for plus c. Okay. Or excuse me, I'm going to solve for the value of c. Okay. So this this power series equals this function on negative 1 to 1, and let's see, the integral should equal this new function on this interval as well. Maybe the endpoints will be different. What I'm going to do is I'm going to pick a value in this interval. Okay, so like x equals 0 is in that interval, right? I'm going to plug it into both sides of this. Okay, and then whatever, so that's going to give me some values on both sides. Then I'm going to have a plus c, and I'm basically going to solve for c. Okay, so let's plug 0 into the left side. Okay, when I plug 0 into the left side, I just get the series 0 over n plus 1, right? Okay, and that's 0 for all the terms. So this is just going to be 0. And then I got plus c, okay, equals the right side. What happens when I plug in 0 on the right side? I got ln of 1 minus 0 is ln of 1. Okay, that's 0. So negative times negative 0 is just 0. So I got c equals 0. Okay, boom. So that means in this particular case, this constant is just equal to 0. Okay. So I can actually conclude that the power series for this function is just this on the interval, let's see, -1 to 1, this interval of convergence. And again, I should check the endpoints, right, to see if it converges at these endpoints. Let's see if I did the if I did the ratio test real quick. I'll do it up here. Well, I don't even need to do the ratio test, right? I just need to test the endpoints. I'm doing extra work here. So how do I test the endpoints? I plug these values into my series. Okay, so if I plugged -1 into my series, what would I get? I would get, and actually something interesting is going to happen here. It looks like if I plugged -1 into this series, I'll do it up here again. I would get the series -1 to the n plus 1 over n plus 1. Is this series convergent or divergent? It's convergent, right, by alternating series test. Again, we should check all our conditions, but it's true. It's convergent by alternating series test. So I would want to include -1. Okay, so this I would have a bracket here, but in my original I had a parentheses. But all right, so this is for x equals -1. What about x equals +1? Okay, then I would get the series 1 over n plus 1. This is divergent by comparison test. Boom. So I don't want to include +1. So my new interval of convergence is -1 to 1. The radius of convergence is still the same. Okay, so now we've seen this technique of integrating and differentiating our power series. And then before that, we saw some techniques of just modifying our power series, right? We can actually combine these two techniques. All right, so let's see an example of that. Let's try and find a power series for this function, 1 over 1 plus 2x, okay? So again, 11.9 is really focused on this particular power series, x to the n equals 1 over 1 minus x. So really, whenever I have an 11.9 for the problems, I think on pretty much all of them, I'm going to try and relate it back to this one power series we know so far. Okay, so how can I relate this to this? Okay, take it step by step. When you see ln's, think it's like the integral, okay? The integral of something like this. Okay, so what is this the integral of? Well, we could try and think through that logically, or we could just differentiate this, right? If we differentiate this, we should get a function whose integral will be equal to this. Okay, so let's see, I differentiate this, I'll get 1 over 1 plus 2x times 2, right? Chain rule. Okay. Okay, so this is the integral of this. Now, can I find a power series for this? If I can find a power series for this, blah, 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 I don't know what it is yet, then the power series from the thing I'm looking for, the power series I'm looking for, should just be the integral of this power series. Okay, so I would just integrate this stuff inside. All right, so the goal is to find a power series for this, integrate it, and that'll give me a power series for this function, which is what I'm looking for. Okay, so now I want to find a power series for this. And remember, it's all about getting this to match this. Okay, so what do I get? Let's see, I got a 2 on top. That's a problem. So I'll pull the 2 out front and write this as 2 times 1 over 1, and then I want a minus sign here, right? Okay, and I got parentheses, so what goes in the parentheses? Negative 2x. Okay. Now, this term looks a lot like this. So now I can modify this power series to match this power series. Okay, or excuse me, I can modify this power series to get a power series for this. Okay, so what's the power series for this thing? Okay, I'm just going to replace the xn with negative 2x to the n. All right. Okay, and then I got a 2 out front. I want to bring the 2 inside. So let's see, I'll start by writing this like this. Okay, now bring the 2 inside. I have 2 to the n here. I bring a 2 inside. I just add 1 there. Okay. Now, the power series for this should just be the integral of all this stuff, all right? But let's take it slow for a second. Remember that this technique of modifying our power series, this changes our interval of convergence, right? Okay, so I know this power series has interval of convergence negative 1 to 1. What about this power series? I do my ratio test. Let's see, I'm doing absolute value, so I ignore the negative signs. Okay, and I want this to be less than 1, meaning I want 2x to be less than 1, greater than negative 1. Okay, in other words, I want x to be less than 1/2, greater than negative 1/2. Okay, all right, so now when I integrate, all right, so this is my interval of convergence for this. Okay, and let's see, I actually didn't test the endpoints, right? So I don't know if they're parentheses or brackets. Let's see if I plugged in. We actually don't need to, I mean, we can do it if we want to be 100% thorough, but we have to check them again anyway once we integrate this. So I won't even write down the interval of convergence. We know it's going to be negative 1/2 to 1/2. It might be brackets on both ends, it might be parentheses on both ends, or a mixture. Okay. All right. So what do we know? We know the power series for this thing. Let's kind of go to a new page. I'm looking for this. I know I know the power series for 2 over 2, 1 plus 2x. Okay, I know the power series for this thing. This is the, let's see, this is the integral of this. So I should just be able to integrate this to get a power series here. Okay. We have this equality on, let's see. Well, again, I don't know the endpoints. So okay, now let's integrate this power series to get a power series for this. Okay, integrating this, let's see, I got a constant. This is a constant, xn. All right, so to integrate that, I would have my constant doesn't change. I would have x to the n plus 1 over n plus 1. Okay, so this is my power series for here. Well, not quite, because I got a plus c, right? Now I need to figure out what this c is. Okay. So let's see. I need to pick an x in this interval of convergence. Okay, again, 0 is in here, right? So I plug 0 into this and match it to this side. Okay, so let's see. I plug 0 into the right side, and I get ln of 1, which is 0. And what should I get on the right side? Let's see. I plug in 0, or excuse me, I plug in 0 on the left side. This whole thing's going to be 0, and I'm going to have a c left over, so c equals 0. So I conclude that this power series is the power series for this. Now, what is the radius of convergence, interval of convergence for this new power series? Well, I know the radius of convergence should be the same as the radius of convergence for this, okay? Radius of convergence for this power series is 1/2. So let's say the radius for my new power series is also 1/2. What's the interval of convergence? I would need to test the endpoints individually. So I plug in, let's see, negative 1/2. It would be divergent. Plug in positive 1/2, and it should be convergent. So my interval should be this. Usually these questions are just asking about the radius of convergence for these integral differentiation questions. So the 1/2 is the important part. All right, so this is, some complicated material we got, but just remember we have two techniques, okay, to find new power series, and we can combine them. Okay, so first technique, I'm looking at, I'm usually starting with this power series and I'm modifying it. Okay, so what are the two ways we can modify it? One, I just, if I'm trying to find a power series for something like this, I try and oh, I wrote this one wrong. If I'm trying to find a power series for a function like this, I try and get this function to match the function I know. Okay, so I would rewrite that as 1 over 1 minus 3x. Okay, so that's one technique. And then the other technique is if I have a function that I recognize as an integral of the function I know, okay, I just integrate the power series. Okay, so I know the power series for this. Okay, this is equal to the integral of this. So the power series for this should be the integral of the power series for this. Okay, and then I need to solve for C. So those are my two techniques. Hopefully you guys were able to follow. Again, I will do another problem video working through many examples.